Um, so first we talk about the divisibility, and first it's the, what is number theory? So, um, integer is fairly restricted class of numbers. It's fairly sparse actually on the number line. It's actually a tiny proportion of the whole thing. But it's very interesting because, a lot of world entity is integer. You cannot count like half person like that, a lot of thing is discrete. So you have to like treat it specially. You cannot treat it continuously. So math involving the property of integer is called number theory. And number theory, one of the most important topic is divisibility. So if n is divisible by another integer m, then reversely, you can say that m is the integral multiple of m. Then um, all the number can evenly divide a number is called its divisor. Then we are also, usually counting the number of the divisor is a topic basically. And primes only has themselves and one. And if a number has other divisors than one, it's called a composite. And uh, a notation, this is a notation, for example, this is called like, it's a vertical line between them. So basically, it's just saying that 13 can evenly divide the 26. And then if the first number cannot divide the second number, then you use a slash to cross out the pipe sign. And so, um, and we have been talking about in the number theory in the previous class on MC8, and it's just the number theory is that basically if you try to write down the divisor of any number, for example 5, this is an easy one, and the way to do that is first count the total. Count the total basically if you just prime factor it. So this is actually 2 multiply 10, 20 equals, and equals 2 square multiply 5. So for each prime number, prime factor, and they are, for example, this is prime like I1, prime 1 I1, prime 2 I2, which P1 is the first prime, P2 is the second prime. Then I1 is the index for the power for prime 1. Then the way to pick how many, it became a combination problem. So how many way to pick the power for each individual prime number, prime factor is like I1 plus 1 multiply I2 plus 1, something like that. So for example, here we know that they are, because the first index is 2 and the second index is 1, we have 3 multiply 2 way, basically it's 2 plus 1 multiply 1 plus 1 way of picking the divisor. So basically we have 6 ways. So if we completely list it, it's going to be 1 multiply 20. And if you start from the smallest one, then like 2 multiply 10, then 4 multiply 5. So this way, I can complete a lesson. Also, it matches the theoretical number, the total of the whole thing. And then this is an easy problem, and it's just listing the prime. And so the prime, especially on the small number of the prime, you actually can use a sift. Basically, you can do a matrix, and then um, then you can filter them out. This is one way. Another way you can test number. So that's the so this is the called sieves of eratosness. So basically you kind of like, for example, you have a matrix and label all the multiple, 2 multiples, 3 multiples, 5 multiples, 7 multiples, 11 multiples, 13 multiples. Then basically you are able to, all the number left, is actually all the green number. Green number are the one, not green number. Let's say that, all the number left is actually the prime number. So that's, yeah. So that's a way to find it in bigger scale. Otherwise, to test whether or not a number is a prime, you only need to test divisor, less than square root of n. For example, in order to test whether or not a number below 100 is a prime or not, you only need to test up to 7. If it's able to, if it's not divisible by 2, 3, 5, and 7, if it's below 100, then it's actually a prime. Because 100 square root is 10. So you only need to test all the prime numbers less than 10. And 7 is the max of those. So this is an easy one. So if you really do it, it's just 11, 13, and 17, and 19. And then the only even prime is 2. This is also a simple fact. So right now we're going to do the number base. And number base, let me do 1 or 2 examples, and we will just do several problems in the class. I'm trying to make sure that everyone understand, because doing the number base, there are 2 types of problem. One is that, convert a number base to, so for example, this is 1, 2, 3, base 5. Let's convert it to the decimals. Another type of problem, for example, if you have a 99 in the base 10, convert into a 8-based x. What is that number? So basically, to do the number-based problem, we need to master the skill of two-way conversion. One is converting from other number base to a decimal. And then, so this is 2 decimal. Then this is 2 other base. Then let me do a few problems just show how to do it. So first, we have to understand the decimal system itself. So how the decimal, for example, if I write down a number called 257, then in reality, we can actually write down its power expansion. The power expansion basically on the ones it's actually 10 to the 0 power, and on the tens it's 10 to the first power, on the hundreds it's 10 to the 10 square. So basically a decimal number is a power-based position value system. So each position, it reuse the digits. It's only 0 to 9. And so the digit, there are only nines or only 10 signs, 10 number value in the ones. But on the higher position or low, even lower positions, just repeatedly reuse it. But depending on where relative position to the decimal point, you know, it's actually represent different thing. Different by what? Different by a tens power. So basically here is actually 2 multiply 10 squared plus 5 times 10 to the first power plus 7. So that's actually its real value. So in the base 7 number, so here we have unit or ones and tens, hundreds. And on the, if it's a 7, basically here is actually the ones. Here is not tens, it's actually 7, sevens. And this is actually 7 squares. This is actually 7 cubes. So basically, you know, basically hundreds is actually 10 squares, and the thousands is just, you know, 10 cubes. So basically it's just, you know, for the convenience of normal communication, because a decimal system is used so much. That's why we design a special name like hundred or thousands to give to like number unit like 10 square and 10 cube. But for other number system, it's the principle is the same. So to convert this into 10 base, we starting the easiest way I think you can do is that, you know, just label it. If you have a different number system problem, just label from the unit place as 7 to the 0 basically is 1, and 7 to the 1 is 7, then 7 squared is 49, and 7 cube basically on this position is 49 multiplied 7. That's going to be 350 minus 7 is going to be 343. So it's 343. So something like that. So if you if you expand the power format, then it actually became 3 multiply 343 plus 4 multiply 49 plus 5 multiply 7 multiply 6 multiply 1. So that's actually the power expansion of this number. So here, uh, let me just cut through the calculation part because I'm trying to just explain it, and so we can go through more of the problems. And so yeah, so basically using the solution. Yeah, so if you multiply it, it's basically it's the 7 base, and based on 7 power, it's a position value system. So it's going to be 1,266. So, and then the second problem, I'm going to show 2 different way. And in this problem, it's only showing a single way of converting it. But in reality, there are 2 ways. Yeah, the second way is actually better than the first way. So I'm trying to show that, like write base 10 problem in base 4. So let's see that if it is a base 4 number, what structure will it has? if it is a base 4 problem, you actually have, this is in the unit is 4 to the 0, then 4 to the first, 4 square, and 4 cube, and 4, something like that, 4 to the fifth. And we need a leading number or next to the leading number. The leading number should be less than the leading position value should be less than 216. So 4 to the 0 is just 1. 4 to the first is 4. 4 squared 16. 4 cube is 64. 4 to the fourth is 256. So 4 to the fourth is already bigger than 216. So I wouldn't use this digit. So if I express this number, base 10 number into base 4, the first digit I'm going to use is on this position. So this is the first method what the book show. I'm going to show you the second way later on after this was shown. And so basically, this is actually top-down method. The first method is top-down. A top-down method is basically, I'm trying to gauge what will be the first digit be if I have to accommodate this number. And this number, because that obviously is too big. If I put a 1 here, it's going to be bigger than this value. That wouldn't work. So I need to represent 216 in base 10 with a 4-digit base 4 number, and the first position, the highest position, it represents 64. So I want to know how many 64 is contained in this number. So 216 divided by 64, I can accommodate 3 with some spare. So that's 3. 3 multiplied 4 equals 12. And this is going to be 19. So this is 4, and this is going to be 24. So basically 3, I'm going to put it here. So that's 3, because that's represent 364 I have on the base 4, and that's in this position. Then I need to represent the remainder 24 with a 3-digit base 4 number. And on this position, it's 16. So I need to ask myself, how many 16 can I get out of 24? So 24 divided by 16. So this can be achieved by division, and remainder is 8. So basically, with the remaining 24, I can spare 116 out. So that's 1. So that's divisor come here as 1. Then I have a remainder 8. 8, I need to represent 8 with the 2-digit base 4 number. And the highest position is 4. So I ask myself how many 4 I can accommodate from the number 8. I can put a 2 here, that's going to be 8. The remainder is 0. So basically I can get 2, 4 here. So basically that's 2. And remainder is 0. So there's nothing to represent. So that's going to be 3, 1, 2, 0 base 4. That's how I get it. And but so this is the second. This is the first method called top down. Actually, a second method is bottom up. Bottom up method is quicker and even more convenient. So basically, the bottom up method is repeatedly divide 4. So the base is 4. So I just divide 4. So basically, 216 divided by 4. So bottom up, I'm trying to get building up from the first digit, from the unit digit. So 1, that's 4 to the 0, 4 to the first, and that's 4, and 4 square, that's 16. 4 to the 4 third, that's going to be 64. So the way I do it is I divide this number by 4. Then I'm going to get 20 and 16. I'm going to get 54. And that's 16 and 0. So the remainder is 0. And 0 will go here. And why this go here? Basically, this is a base 4 system. And the unit position basically will be the remainder of the division by 4 with the whole number, because if it is, for example, imagine if it is 217, when you do the whole thing, you actually will get remainder 1. And that 1, because any higher position above this is actually a 4 multiple. So if I have a number here, for example, 1, it's actually 1 need to multiply by 4. And this position is actually whatever is left over that cannot be evenly divided by 4. And if, for example, if it's a 4 base force number with unit number 0, means that this number is actually a 4 multiple. Like in the decimal situation, if you have a 810, means this number is a 10 multiple. And if you have 812, the 2 is the number 2 is the remainder if 812 divided by 10. So basically it's the same principle. So on the base 10 system, the unit digit represent the remainder divided by 10 if you really do the division. And also in the base 4, any base, the unit digit represent the remainder divided by that number base. So basically, just by dividing 4, I get 0, means that, 216 is actually indeed is multiple of 4. So the remainder is, or the divisor is 54. So divided 54, I will divide 4 again. So that's going to be, and that's 12 and 2. So this 2 will go to here. The 2 actually will go to the 4th. Why? Because 54 is the multiple I need to multiply 4 to get 216. And then if I divide by 4 again, whatever the divisor here, basically it actually is 13, multiply this 4 and multiply this 4. So basically I actually has 13 multiply 4 square or 4 square with those two division. And this 2 is the portion of the number that not, this 2 is the portion of the numbers that is multiple of 4. It is for 4 multiple, but not 4 square multiple, because 4 square multiple will actually come up on this divisor, not the remainder. Remainder basically is the portion of the numbers that successfully passed the first division but got filtered out on the second for division. So basically, that's why the remainder goes here. So, if you really think logically, the 2 is the portion of this 216 that is multiple of 4, but not multiple of 16, not the multiple of 4 square. So that actually comes here. So right now we actually have 13, and the 13 is divisor. We divide by 4 again, then we actually will get this. And so the portion 1 is actually, multiple of 16, but not multiple of not multiple of 64, because this actually come out of 13, which is, multiple of 2 of 4. So it's the remainder is, is portion of the number that represent multiple of 16, but it failed to evenly divide this 4. So this 1 is not the portion of the numbers that goes into the uh, 4 square. So that's actually 1 goes here. Then the last is 3, and 3 is actually less than 4. So basically I don't have to do division again, just can go straight here, because this 3 actually is multiplying 4 here. Then the number in the build up will be 54. It's going to be multiplied 4 again. If we reverse construct, then it's going to get to 54. Then it's going to multiply 4 again up to 216. So basically this 3 is the result of 3 division by 4, and then 4, and then 4 again. So basically this 3 actually, is entitled to have 4 or 3 of the 4 factor, 3 of the 4 so basically it's actually need to multiply 4 to the cube. So basically, if I repeatedly doing the division, we can do the bottom up, because each remainder is actually the portion of the data that, um, failed on the next level division, but pass through these levels of number of the 4 division. So basically actually goes snap into this. So this is actually an easier way. So basically, for me, I usually always use the second method, but the book tell you only the first method. So basically, hope you will learn both. And let's kind of do the um, let's trying to do a few exercises. This is especially those 2 exercises, really simple one. And let's see, how everyone one will do. Let's trying to do this problem. Let's give everyone 2 minutes to see if how it will go. So find base 10 representation of 4, 7, base 8, 4, 7, base 9, and 4, 7, base 16. So there are 3 little problems here. You can chat me if you finish the problem. Okay, I think time is up. So let's see. Like no, looks like no one chatted me. So I assume that there might be some difficulty, and let's just review it and how to handle it. So for all type of the number-based problem, let's just do this. For example, 4, 7, let's space out a little bit, this 8. So this is 8 to the 0, that 8 to the first. So this is the multiple you're trying to multiply. And if you have another number, for example, this is 6, then basically 8 squared. So something like that. So let's just deal with this. So this is just in the ones, this is 1 and 8. You can further expand it to the real number without the power, but this level you can just write a power. So make sure that you are not making a mistake. So here is 1 multiply 7 is 7, and 4 multiply 8 equals 32. And so this is you plus it, going to be 39. So that's the answer for this problem. And then we have 40, we have 4, 7, base 9. You cannot call it 47. It's not 47. 40 means that 4 of the 10. It's just 47 base 9. And or you can say 497. Basically, it's actually, you know, a different base. It's different calling. So that's 9 to the 0 and 9 to the first. And this is 1 and 9. So 1 multiply 7 equal to 7. 4 multiply 9 equal to 36. So that's going to be, if you add it, and 43. So basically, you know, so how to do this type of problem? First, you add a layer on the power expansion. Then you basically expand it. Then you do multiplication. And this, it's a 16 based. 16 base basically. 16 base, you actually have, you know, a 16 digits. And 16 digits, so it's going to use, you know, a letter to represent number. So it's going to run 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, and F. And 10, A is 10, B is 11, C is 12, D is 13, and E is 14, and F equals 15. So that's the way you represent the 16 base. So 16 base, but we are not using the letter yet, but you know, you should be able to do, so that's 47, and this is 16. So this is 16 to the 0 and the 16 to the first, and this is 1 and the 16. So if you do multiply, it's going to be 4 multiply 16 plus 1 multiply 7. And so that's going to be 64 plus 7 equals to 71, 10 based. So that's the way that you can do this. And okay, so let's try to do this one. And so this is just, you know, find base base 8, 9, 16 representation of 47 10 base. Right now I can call 47 because it is 10 based. And okay, let's also trying to do this problem with 2 minutes. Give it a try and see if you're able to do it. Okay, time is up. Looks like also no one chatted me. So let me show how to solve this type of problem. So right now we go from 10 base to a different base. So if it's going to be 8 base, it's going to be 8, 0, and 8 first, then 8 square. I don't know which one is going to use. So basically, I'm going to expand. This is 1, 8, and 64. And 64 is bigger than 47, so I'm sure I'm not going to use 3 digit. I only need 2 digit to in base 8 to represent 47. So that's the first information. So I can do two-way. Let's say top down. Top down basically, the first thing I need to consider is how many the top position it can accommodate. So 47 divided by 8 actually is the 40, and that's 7. So basically I can accommodate 5 of the 8. So that's 5. And then after 5, 8, I got a 7. So basically in this case, I got 57. And the second method, so right now, because it only has 2 digits, so basically the first method and second method is the same. And if it is, but the first method basically, a little difference is that if you have a bigger number, for example, if I have a 89 like base 10, then I will not divide 8 because the largest number is 64. I need to divide 64 first. So basically the top-down method, because this is just coincidence that, the leading, number can be already handled by dividing 8. I don't have to divide 64, so it looks the same, but in reality, it's not. So bottom up, basically, I don't even consider anything. I just divide 47 by 8. The remainder is 7. So this is bottom up. Bottom up, basically, I got 7 divided by 8. I got 7, and remainder, or the divisor is 5. Divisor 5 is already less than 8. So basically, I just put 7, 5. So this is top down. I divide by 8 because I may divide by 64 or may divide by like even a bigger number. Then if I divide by bigger numbers, then I will put down the divisor first, and bottom up you put down the remainder first, and then you put down the divisor only if the divisor is already less than the number of the base. Number base is 8, so if the divisor 5 is less than 8, I can put it down. So this is the bottom up. And for those 3 problems, basically top down and bottom up are literally the same because because on 9 you still do the same. Is 9 0 9 first and 9 square, and you do a few just to accommodate 47. So this is 1, and this is 9, and this is 81, and 81 is bigger than 47. So basically, I no longer need to do division on 81 because this number too small for it. So basically 47 divided by 9, and I got remainder 2. So basically, top down, I write 5 and 2. And bottom up, I write 2, 5. So basically, either way, it looks the same. And then let's do the last problem. That's 47. Use the 16 base. 16, I got 16 to the 0, 16 to the first, 16 square. And this is 1, this is 16, this is 256. 256 is bigger than 47, and 47 is bigger than 16. So basically we're going to start using 16. So 47 divided by 16, I got 2, and 32, I got 15. So 15 is the remainder, and 2 is the divisor. So if you use top down, you got 2f. Or if you bottom up, you got f2. So basically, either way looks about the same. Hope you really master it, because yes, it's actually kind of important. You actually do, especially doing the computation, you do need to know how to do it. And so looks like this might be a weak point. So just trying to do those problems and getting used to it. And so again, there are two methods, top down and bottom up. Bottom up is a little bit easier. You just dividing the number base and put the remainder one by one until the divisor is less than the base itself. Then you put on the last is, so this is the remainder, then the last is divisor. Then top down, basically you are trying to divide the highest possible power. So you go from like dividing the highest power, for example, in this case is a fairly big number. Yeah, 64. So I'm dividing 64 first, and then divide by 16. So these are divisor and divisor, divisor. Then the last one is the remainder. So basically those are, and each time you dividing by a divisor, it's a power, it's a different number. It's you did divide the highest power number first. And so there seems to be, the first method seems to be a little bit more complicated. And the second method is actually much easier, much more smoother. And you can do both way, and I recommend you are able to do both ways. So you can do one problem this way, then double check using the other way. Okay, so let's keep on going. And so this is actually an interesting question. How do you multiply a number or how do you multiply a number by 2 in base 2? So basically, this actually, you can expand the problem. How do you multiply a number by 3 in base 3? How do you multiply a number by 4 in base 4? How about you multiply a number by base 10 or by 10 by base 10? If you reach the last question, it's very easy. When you multiply a number by 10 in base 10, it's just adding a 0. So if you think about this, it's actually the same with all the other number base, because multiply a number by 2 in base 2 basically is just equivalent to adding a 0. Basically, for example, number 2 or base 2 number, for example, is 11, base 2. You actually cannot call it 11. It's just 1 base 2. 1 base 2 here is just 1, 2 to the 0, 2 to the first. So basically this is 1 and 2. And if you have 11, basically if you multiply it, it's going to be like 1 plus 2 and equal to 3. So basically 1 base 2 is actually equal to 3. So if you multiply it, if you multiply by 2, so 3 multiply 2 equal actually 6. So let's convert 6 into base 2. And convert that back in base 2 basically is 6 divided by 4, because base 2's, this is base 2 second power, and you actually got 1. So basically, then the remainder is 2. 2 basically is just first power. So basically 2 to the first power. So 6 you can write into 4 plus 2 and equals to 1 multiplied 2 square plus 1 multiplied 2 equal to 110. So basically in base 2. So basically, we can double check with extremely easy number and looks like, if we multiply 1 base 2 by 2, 2 basically in the one in 2 in base 2, basically it's 1 0 base 2. So when you do this, if you are multiplying looks like a 10 in another base, basically just equivalent to adding a 0. And we actually use the decimal conversion back forth to check it, and it's actually true. So this and so then basically it's the last digit problem. Last digit problem is actually an extremely easy one. So last digit problem, when you are doing multiplication and addition, and the only thing matters to the result on the last digit is the operation of the each participant on the last digit. So a lot of problem, especially the power problem, addition problem, if the question is just asking the last digit, you don't really to do any operation on other digit. For example, let's say that what is the last digit of 34 multiply 17? You actually you only need to multiply 4 multiply 7 equal 28. So 8 is the last digit of 34 multiply 17. And then addition, for example, is likewise. So basically 4 plus 7 equal to 11. So basically the last digit of 34 plus 17 equal to 1. So here comes the question on, all the possible value. The square of integer not to be. So in base 10, we have 10 possible integer number ending. We can end with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all the digits we can end with in base 10. If we power the last digit, we got 0. So anything end with 0, if you power it, it's still going to end with 0. Then 1, you got 1. 2, you got 2 square equal to 4. 3 square equal to 9. 4 square equal to 16. So I only need to write down 6. And 5 square equal to 25. So that's write down 5. 6 square equal to 36. So 6. 7 square equal to 49. So that's 9. 8 square equals 64. I write down 4. 9 square equal to 81. I round down 1. So basically, you will see that 0 is a possible outcome. 1 is a possible outcome. And there's no 2, there's no 3. Then there's a 4 and a 5 and a 6 are possible outcome. Then there's no 7 and no 8. Then 9 is also a possible outcome. So basically, any numbers, any integer square, the last digit always end up with those number. And the question is asking not to be. So not to be, basically that's 2, 3, and 7, 8. So the last digit of a integer square cannot be end with 2, 3, 7, and 8. So this is a problem that you might think very difficult, but in reality, it's not, because it's asking the high last digit of 2 high power. So we have to understand how the power works. The power of last digit always follow cycle. So there are cycle of one period one, and cycle period 2, and cycle of period 4. So those are 3 type of the period we are dealing with. And so cycle of period 1, that's easy because that's like 6, because 6 square, end with 36. So last digit is still 6. So in fact, 6 any square will end with 6. So is 1. 1's any square. So that's period 1. We have 0 also is 1 is 5 and 6. So basically those are the 4 number with period 1. And period 2 basically is the numbers that a ping-ponging between, and 2 period number are a perfect square number, basically is 4 and 9. And under, 1 digit number, and 0, 1 is also perfect square, but those actually, period 1. So for the period 2, the only 2 number are like prime number. You can call it a prime number perfect square. Prime number perfect square in digit world, in the unit digit world, there's only 2 of those, 4 and 9. So because 4 square going to be equal to 16, and 16 multiply 4 equal to 64. So when we just multiply 4 up and up again, it start at 4 and goes to 6, then it go back to 4 again. So it's actually ping-ponging between 6 and 4. And so is 9. So 9, this is 9 to the first is actually 9. 9 square equal to 81, and 9 cube equal to 1 multiply 9 here is actually something 9, basically, actually 729, but it still ends with 9. So basically the ending number is always 9191, something like that. So this is the period 2 is the prime perfect square. And period 1 is 0, 1, 5, 6. Then the remaining number are period 4. So basically that's 2, 3, and 7, 8. So 2, 3, 7, 8 basically is period 4 power sequence. And you don't really have to remember it. You actually, I never remember it, but just by putting understanding behind it, this you can test it out fairly easily. You can find it right away. I don't remember it, but it's 0, 1, 5, 6. I can perfect prime square, and that's the remaining is just period 4. And period 4, basically, let's just check, like, so period 4. So we altogether we can build a very simple table. Like this is 1, 2, 3, 4. So this is 2, 3, 7, 8, and 2 to the first power is just 2. 2 to the second power, 2 squared is 4. 2 to the third power is 8. 2 to the fourth, 2 multiply 8 equals 16. So 16, I go back to 6. I'm going to ignore 1. And because we are only care about the last digit. Then on the 5th digit, I just add 1 colon, just make sure that I'm going to cycle back, repeating the pattern. So 2 multiply 6 equal 12, and the last digit is 2. Indeed, I go back to 1. So at 5, it's going to go back to 1. That's for all those 4 period thing. And that's 3 to the first is 3. 3 square equal to 9. And 3 multiply 9 equal to 27. So 3 cube is 27. I just put on last unit digit. And 3 multiply 7 equal to 21. So that's 1. And 1 multiply 3 equal to 3. So basically, I always at position 5. If you power 5, it's going to repeat its pattern here. And 7 first, 7 square 49, so that's 9. And 7 multiply 9 equal to 63, so that's 3. And 7 multiply 3 equal to 21, so that's 1. And 1 multiply 7 equal to 7. So basically, after 4 periods, for 7, it's rotate back to 7. Then we have 8. So 8 to the first, 8 squared equal to 64, so that's 4. And 4 multiply 8 equals 32, so that's 2. That's what cubes end with. And then 2 multiply 8 equals 16, so 6 here. And 6 multiply 8 is 48, so 8 going to rotate back. So basically, it's just this table. Then this is quite important. 4 is also 0, basically. 4 is 0. You have to understand that, because that's because we are trying to match the mod 4, index mod 4 value. For example, like 42 is congruent to mod 4. And so we're looking for the ending of 742s. So 7 to the 42s, that's going to be 9. So basically, then 42 to the 7th. So 7 is congruent to, and 42, what we are checking is this line. And 42, 7 is congruent to 3 mod 4. So basically, 2 to the third power, 2 to the third power is 8. So basically, this is 8. This is going to end with 8. And the first one, congruent to 2, so it's end with 2. Oh, and end with 9, because it's 7 to the 2, 7 to the square, end with 9. So 9, and this is 2 power 3. 2 power 3 is 8. So 9 plus 8 equal to 17. And then the last unit, the unit digit is going to be 7. So that's the way you find it. So this is using the modular math. And there is individual reasoning. You can always reason your way, but I find this is more consistent. So basically, if you understand the period, the power period, like 1, 2, and the standard answer for this problem, basically, yeah, the standard answer for this problem involves certain reasoning. So basically, you just power 7. You power 7 by 4 times, you end up with 1. So basically, 7 to the 4th will end up with 1. So 7 to the 4 multiple, 7, for example, 4 multiply 10, that's going to end with 1 also. So basically, because we use up 40, the power 40, we can write that as 40 plus 2. So the 40 power end with 1, then only the last 2 power really matters. The last 2 power matters, so that's 7, that's square. So 7 multiply 7 equal to 49, so that's 9. So basically that 9, that's how it used the reasoning to get it. And then this assume you have no knowledge of the numbers property. And if you do the first time discovery, that's great. And or if you totally forget about the theoretical result of 4 different period, and then this is also a good way to reasoning. Then for like 2, basically, you know, uh, it's just result to like 2 to the 7th directly, because you can get rid of the first 2. You are only care about last digit. And for 2 to the 7th is actually easy to power. You got 128, so you actually just got 8. So basically, in terms of this type of problem, this this method, it's used recommended on the solution is just much more random, much more unsystematic. So it's just use a random calculation, but either way, it's fine. And as long as you are able to figure out, that will be great. But knowing the number repeating pattern, basically, you take out a lot of guesswork, and it's just matching. So for 42, it's just matching the end with 7, because it's 42 congruent to 2. So basically the 2 ending, and this is 4, this is 42. 7 is congruent to 3. Congruent to 3 means that, if you 7 divide by 4, your remainder is 4. So or remainder is 3. So so this is 2, because 2 congruent to 3. So basically you just map it to here. So basically using the cycle of period table, you can just focusing on listing this correctly. Then the remaining thing, you can just first match the last digit. Second, match the congruent power index. Then you will get the end digit value directly. So that's the way I usually do it. Then we're going to talk about modular math. And modular as arithmetic is actually quite useful in terms of simplified problems. Like the last problem when we, the standard answer it gave to the complex problem is not using the modular math, but the way I using period actually is using modular math. So modular math, how do we spell this this notation? So why modular math? You would ask the question, because we talk about different number base. For example, if we do all arithmetic in base 5, then we will find that the last digit could be the same. For example, 2 base 5, 1 2 base 5, 2 2 base 5, 3 2 base 5, basically they all end with 2. They end with 2, all it means is that just this number, these number actually divide by 5, divide by 5, remainder will going to be 2. Remainder going to be 2. So for example, if you have a decimal number, for example, if a decimal number end with 3, no matter it's 3 or 93, or it has to be positive, okay? Negative will be totally different game. So, and then if it's negative, it's going to be -7. For example, -7. And if 3 minus 10, going to be -7. And then like 10,003. So all these number has some common common property in terms of the number is that, dividing by 10, still remainder is 3. So, and for this, divide by 5, remainder 3. And if you express those number in the decimal, so this is 2 base 5 in the decimal, 2 base 5 in the decimal. 1, 2, basically it's just 5 multiply 1 plus 2. So basically it's 7, and this is 12, this is 17. They are all congruent. They are all congruent to 2. So here is how you read it. 12 is congruent to 7 mod 5. So that's how you read it. The meaning of this sentence is just means that 12 and 7, if they divide by 5, will have the same remainder. So that's all its meaning. And usually people, when doing this type of problem, they prefer the smallest modular number, smallest positive modular number. So basically, it's actually also congruent to 2, basically. So here is like the mod number, if they congruent. So that's 2, 7, 12, and really pay attention to the negative direction. The first negative number you actually will be subtract 5 from the smallest positive modular number. Then you just consecutively minus 5 to go the other direction, and you will get all the possible negative values. And notice that negative value and the positive values, they don't end with the same, usually they don't end with the same trailing number. So modular math also follow like equation. So for example, here is 12 is congruent to 7 mod 5. And if I add both sides by 3, the whole thing still stands. So basically S3 on left side, on 3 on right side. So basically here, if we really do the calculation, 15 is congruent to 10 mod 5. And the last digit operation works for addition and multiplication, but the mod number not necessarily work for the division. Division is a totally different ballgame. For example, division is quite complicated. And so 5 is, so here is a counter example. The counter example is 5. 5 is congruent to 10, is congruent to 0, actually mod 5. And so you cannot, for example, say divide 5 on both sides. If you divide 5 on both sides, then you will say that, and 1 is congruent to 2 is congruent to 0 mod 5. And obviously this is ridiculous. And why divide by 5 or multiply 1/5 on all the equation side do not work, because actually 5 is actually congruent to 0. So basically when you divide by 5, you can also say you're actually dividing 0, and dividing 0 is not allowed. So basically division on, when you do the modular math, usually just do addition, subtraction, and multiplication, and the powers, those are all fine, but just avoid doing the division, because the division, even you are not dividing by 0, you actually could be dividing a equivalent value of 0 in the way. For example, right now I'm dividing by 5 or multiply 1/5. But this 5 on the denominator is actually also congruent to 0. And when you're doing it, it's actually you're dividing 0, you're introducing something prohibited. But on the modular math, it's quite easy to make mistake if you use division. So avoid using division in terms of the. So here we has a lot of important result as of modular math. So here we make the assumption we have two pair. If A is congruent to B mod M and P is congruent to Q mod M. So pay attention, that works if they only, you know, the equation or congruent sign apply to the same modular number. Modular number basically is the divisor you are using. So basically when you talk about those equations, you need to do division on both the same number. Otherwise, if you divide by different number, try to mix match, it's not going to work. And none of those operations will work. And so here, basically, A and B are congruent. Then you can add any number because those are, so the modular operation equation still work. Minus also the same, you can add the same number, minus the same number, multiply the same number, square them, and but 1, 2, 3, 4 obviously don't see dividing by the same number. That's not allowed. And then you also will find that if you have a pair of congruent, so A is congruent to B and P is congruent to Q, then we have two pair of congruency relationship. Then adding them by pair is also congruent. Then if I have a two pair of congruent relationship in modular M, then multiplying by pair also works. So those are the important. You don't really have to remember it. I never have to remember it. It's just, it works because you know the only thing not working is division, so you can just use other things freely. So this is an easy question. Write down some numbers that are congruent to 3 mod 5. So obviously, if you have this type of problem, the first number is just 3 because 3 is, congruent to itself. And then you just, by doing this adding or minus 5 and my adding and minus multiple of 5. So add 5 is going to be 8. So minus 5 going to be -2. And so then you minus 5 again, it's going to be -7. So you add 8 again. So or add 5 again, you actually got 13. So basically just starting from 3, you adding or subtracting a number, you will get the list. What is the largest integer less than 100, which is congruent to 3 mod 5? Let's try to do this problem given like 1 minute. Let's see if anyone can get this one. Okay, time is up. Anyone get the answer? Okay, so let me just show how to do this. So here, largest number less than 100. So basically it must be like 90 something, is that right? And 90 something, and you can just try it directly. One way is that, you can say that, I can, if you do it directly, you can do like 98. Basically, you want a remainder 3 divided by 5. So I know that 95 is one of the integer. If 95 plus 3, which makes, because 95, 5 divides 95. So basically, plus 3, 98 is 1. So you can also do like 100. I know that 103 is congruent to 3 mod 5. And then, but it's bigger, a little bit bigger. So if I minus 5, I also going to be get 98. So there are two ways of getting it. So this is the first way is just, trying to search in the the few close to max number, because the max number is 99, but that one do not satisfy, is not congruent to 3 mod 5. So congruent to 3 mod 5, all it does is just like, this number, let's say x equal to 5m, n is an integer plus 3. So that's basically, what it's saying. And so let's try to do this problem in 1 minute. How many positive number less than 100 are congruent to 3 mod 5? So it's positive number, so not including 0. So it basically less than 100. So basically it's asking between 1 and 99, how many number are congruent to 3 mod 5. Okay, anyone get this one? Looks like, oh, oh, the difficulty on this problem, no worry about it. Let me try to explain this thoroughly. How many positive number are congruent to 3 mod 5? Basically, it's asking that, how many integer between 1 and 99, 1 dividing 5, 1 divided by 5 has remainder 3. So basically, uh, I think the terminology is still kind of get confusing everyone. I think, this is actually important. You have to understand this system to excel in the number theory. So let me try to go over this again. So for example, 12 is congruent to like 7 mod 5. So basically, the modular math works this way. One, it's asking this problem, like, what's the smallest number that, you know, is congruent to 3 mod 5? That's 3. So 3 is congruent to 3. And because 3 divided by 5, and you can put a 0 as a divisor, and the remainder is just 3. So basically, you know, 3, 1 dividing 5 has remainder 3. So basically, this is just its meaning. Then you will see what's the next number will be having remainder 3. Obviously, it's 8, because if you 3 plus 5, then 8 divided by 5, you put a divisor 1, then you got 5 and 3, you know, so 1 is the quotient and 3 is the remainder. So 8 is congruent to 3. In fact, you just keep adding the modulo numbers, you will get the next one. So basically, you just keep adding 5, then add 5 again. So this 13 is congruent to 3 mod 5, and mod 5, and then 18. So basically, when you make this observation, you know that, you know, it's for every gap of 5, you actually get a number that congruent to 3. And what is the last one? Obviously, it's going to be 98. So you from 3 to 98. Then the problem turn into from 3 to 98, how many number you have if the gap is 5. So the gap 5 is 98 minus 3 equals to 95. And 95 divided by 5 equals 19. So there are 19 gap. A 19 gap, but because we are counting the number, so it's like a telephone pole or light pole problem. How many gap? The pole number is always one bigger than the gap number. Starting from, like, you know, if you have two pole come with one gap, so 3 pole come with 2 gaps. So so the pole number is big. So when you do this, it's actually, you know, 95 divided by 5 equal to 19. 19 plus 1 equals 20. So basically, this number, how many positive number less than 100 are congruent to 3 mod 5, that's going to be 20. So 20 is the final answer. Okay, so let's go to the next one. Let's see. This is going to be a similar number, a similar problem. Let's give this problem a try. You know, because I just explained this problem. Hopefully this one will make a little bit of sense to everyone. So how many integers are there between 50 and 250 inclusive, which are congruent to 1 mod 7? So let's count down 1 minute. Thank you, Tracy, for giving the feedback. I'm glad you understand it. It's really very valuable if you are able to, you know, chat me on the explanation. I really hope everyone can understand. This part is important because it's the contest, in the contest, it's just full of this type of problem. You are guaranteed to hit a lot of those problems always. So basically, we have to fully understand the modulo, you know, sign and their meaning and their operation. Okay, time is up. Anyone get the answer?
Can you give me a little more time?
Okay, let me give you a little more time.
Okay, thank you.
Okay, that's good. Very good. And so let me show how to do it. And um, there are correct answers, there are wrong answer, but either way, no matter how you did, don't worry too much about the result. And you if you gave it a good try, and I respect all your effort. And let's trying to do this. So this is actually the way is that what number is mod 1 or is congruent to 1 mod 7, actually 50, because 50 divided by 7 is actually 49, is 1. So basically 7, so 50 is the starting number and it's actually satisfied. So we kind of just add 7, and until we hit a range which is below 250, and then we will just go with the numbers at above 250. So how do we do with this, because that's actually quite difficult to gauge, and you have to do a lot of guesswork. So basically what we are trying to do is that you know, use the definition of modulo. Definition of modulo, basically, it is just, 7, you know, k plus 1. Basically, 50 equal to 7. In this case, k equal to 7. 7 multiplies 7 plus 1. And then we're trying to do 250. 250 may not be modulo 1, but we're going to be use the 7 and trying to find its remainder. So 250 divided by 7 is 21, that's 40, and 35 and 5. So basically 250 going to be 7, multiply 35 and plus 5. So basically, and so we know that the last number. So what when you counting the gap problem, basically you actually have to, when you counting the gap problem, you have to do the clear starting and ending. So clear start and end. So the clear start 50 already there. So the clear ending is actually going to be 7 multiply, because it's going to be less than between 250. So it's going to be 7 multiply 35 plus 1. So plus 1, the difference between 50. So it's going to be 240. So there's a 4 difference. 5 minus 1 equal to 4. So this is 250 minus 4 equal to 46. So basically, the first number is 250. The last number is 246. So this is a clear cut. So we don't use those numbers to do the division, because we actually have to use a clear cut number. And if you use the clear cut number to do the counting, it's going to be accurate. So 246 minus 50, that's going to be 6. That's going to be 196. So 196 divided by 7 is equal to 14, and that's equal to 56. And this is 56. So there are 28 gaps. So 28 is the gap. And because we are counting the number, including the first and last, it's going to be 28 plus 1 equal to 29. So 29 is the correct answer. And so that's Yeah. So this one is a easy exercise. Which number are congruent to 0 mod 5? So this number basically is actually, you can do this, you know, according to the definition of the, congruency in modular mass. Basically, the numbers actually k, 5k plus 0. So basically, that 0 is a congruent number. So it's just 5k. What number congruent to 0 mod 5 is actually 5 multiple, 5k, and k is, belong to the integer. I have to write so so this is 5 multiple congruent. So this actually is a key property. So if a number is congruent to 0 mod any number, mod any, so basically it's just any multiple. For example, here, if we are given A is congruent to 0 mod B, then A is equal to KB. So basically that's multiple. It's equivalent. So those two things are totally equivalent. And that is why, the modular mass and modular sign is a very valuable tool in dealing with this type of the problem. And so we are going to do a few problems that um, this type of the problem is, yes. So I'm going to show you how to use the modular mass. So this going to be the last problem we're going to teach today. We're going to stop at the modular mass because today we actually hit two topics. The first is the number-based conversion. Number-based conversion, I'm going to make up a few problems. So hopefully you totally understand more, number conversion, because it's not just useful for math, it's also useful for computer science. Computer science use a lot of binary conversion, use a lot of hexadecimal conversion, use a lot of octal conversion. So basically, in computer science, it does convert a lot of base. It's one of the basic for, like, also use binary conversion. So and so this one is actually the way to correct use the modular mass. If a set of marker is placing a row of 4 each, there are 2 markers left over. So basically, um, if row of 5 each, there are 3 left over. And if row of 7, then there are 5 left over. What is the smallest number of markers that the set could contain? And this is a very, very typical modular mass problem. So I'm going to write this down and just show you exactly how to use modular mass to solve it. And there are similar problems in the problem set, just trying to follow exactly what I'm doing, because that's the correct way of doing it. And that's quite important. So this problem, pay attention. And so basically, if I trying to get the smallest number of the marker, so I can say that the marker is actually congruent to mod 4, because you arrange them in 4 each row, and there are 2 left over. So basically, this actually equivalent to be m is divided by 4. It will end with some number, let's say I, and then the remainder will be 2. So basically, this, the way it's stated, just mathematically express it, it will be this way. And if rows of 5 each, there are 3 left over. So it's m is congruent to 3 and mod 5. And row of 7, so it's going to be row of 7. So 7, so pay attention that row of 4, so that's 5 is 4 divisor. Row of 5, 5 divisor. Row of 7, that's 5 divisor. So there's a divisor and remainder. So divisor go here, remainder go here. And remainder I'm going to use a different color. So this is the remainder goes here. And then this m is congruent to 5 and mod 7. So here 7, row of 7, you are dividing by 7, and 5 is a remainder. 5 goes here. And row of 5, 3 left over, so that's where it goes. So after all those manipulation, I still have no clue of m. But the modular mass strength does not happen when there's 2, 3, 5. Modular mass is only powerful when remainder is 0. This you have to remember very clearly, because here this is very, very important for any modular number. If a number is congruent to 0, then that number is this modular number's multiple, integral multiple. So that's extremely important, extremely important. So what happened is that this is very much useless at this point. But what we are going to do is we're going to make this to be 0. How do we get 0? We add 2, because 2 plus 2 equal to 4. And in modular 4, 4 is congruent to 0 mod 4. And here, if we plus 2, 3 plus 2 is going to congruent to 5 is congruent to 0 mod 5. And here is 5 and it's 7. So 5 plus 2 is congruent to 7 is congruent to 0 mod 7. So basically, adding 2 on both sides is actually going to make the whole difference. So basically, m plus 2 is going to be congruent to 0 mod 4. And m plus 2 is going to be congruent to 0 mod 5. And m plus 2 is going congruent to 0 mod 7. So basically, m plus 2. And right now, we look at m plus 2 holistically. Just treat them as the whole thing. We no longer dealing with m. We're dealing with, because by dealing with m plus 2, we are dealing with simultaneously. It's simultaneously 4 multiple. It's simultaneously 5 multiple. And simultaneously 7 multiple. So basically, m plus 2 is actually equal to 4 multiply 5 multiply 7, because 4, 5, and 7, those are mutually um those are mutually have no common factors. So those are co-prime. Those are co-prime factors. So if they are co-prime factor, you just stack them up. So n plus 2 equals 4 multiplies 5 multiply 7 multiply like I, something like that. And I want the smallest number, so the I has to be 1. And so basically, I want I equal to 1, then the whole thing is 20 multiplied 7 equal 140. So m plus 2 is 140, and m equal to, I'm going to minus 2 on both sides, it's going to be 138. So by using the modular math, what we find is that we cut through all the troubles and find the modular zero value, and zero value that can turn into action of divisors multiple. So modular math is just a dividing problem, and when the congruent value to be zero, that's just multiple. That became powerful. So that's a typical problem, and you're going to find a lot of those problems. So it's from time to time they will just arrange things and do this way and that way, and it's going to you know um, sometimes is easier problems. They actually have just every way the row of sevens is one left over and one left over or one left over. And this time it's 2, 3, 5 left over, but it's just by adding you are able to get to the next modular value to get 0. So basically it's practically just those two way, but either way it's using modular math, and multiples used here is a key to solve the problem. Okay, I think that's all for today. And um, the number theory still have some content, and I'm going to also like pull back some of the problems and content in the last time's middle school competition math, so that review plus and learn something. And okay, have a nice one, everyone. Bye bye.